It's 5:30, and this is the 17th week of class, and this is our last class meeting before finals. Okay, so just so you're aware of what's going on this week, we meet today for lecture, and that's it. No labs this week, no Thursday lecture, because Thursday is when finals week actually starts. Our final exam is not until next Tuesday, so we're exactly a week away from the final, all right? So if you haven't done so already, pick up a copy of the review packet for the final exam. It's up here. You can get it now or after class. And just as before, use these to study for the final. Go through these problems. If you're comfortable with all the problems in the packet, you know how to solve them, you should be in really good shape for the final, okay? I'm going to post the answers to these questions with fully worked out solutions to Canvas, I think on Friday of this week. All right, so that's when you can expect those to go up on Canvas. Because we don't have lab meetings this week, we're not going to be doing these in lab, obviously, but still use these to study as you normally would for any other sort of test. Okay? So with that said, let's get back into the course recap lecture. And we covered kinematics last time around, so now we're going to move on to Newton's laws of motion. All right, so let's briefly just state what they are. Okay, we have the first, second, and third law of motion. But what you see we have here all together is sort of a framework for analyzing motion, okay? In this framework, we say forces are the causes of motion. And if we completely understand the forces that act on an object, then we can predict how it's going to move. So it's a really powerful set of rules which basically allows you to predict the future, how something is going to move if you know what's acting on it. So the first law is what's known as the law of inertia. And this states that as long as we're in an inertial reference frame, that is a non-accelerating reference frame, the following is going to hold true. An object's velocity remains constant unless acted upon by an unbalanced force, right? That is to say, if an object has completely balanced forces, in other words, zero net force acting on it, it's going to move at constant velocity. The second law deals with what happens when you don't have completely balanced forces. This says the net force acting on an object determines how it's going to accelerate. According to this equation, the net force equals m, which is the mass of the object, times a, the acceleration. So this is really the workhorse for solving problems. Use F equals ma a lot, okay? Now the third law concerns interactions between two different objects, all right? So when two objects interact, they exert forces on each other. And these forces are always equal in magnitude and opposite in direction. So we can put this using some notation as FAB, that's the force that object A exerts on object B, is equal to minus FBA, that's the force that B exerts on A. So the forces are the same up to a minus sign, meaning they have the same magnitude, but they point in opposite directions. So just a really quick example of that, right? If I push down on this table here, the force I exert on the table is downwards with some strength. The table is exerting an equal and opposite force upwards on my hand, okay? And every force comes in pairs just like that. Okay, so those are the laws. But if we're going to effectively use the laws of motion to solve problems, we need to be familiar with the various types of forces that actually exist out there in the real world, okay? So some of them that you should know about are, for one, gravity. So gravity is an attractive force between two masses, and we have sort of different ways of treating gravity, right? We have gravity near Earth's surface, and then gravity more generally, as stated by the law of universal gravitation, which we'll get into in a second. We also have normal forces. So whenever you hear the word normal, just remember that means perpendicular. So a normal force is a force that a surface exerts on another surface. What's the direction of it? It's perpendicular to that surface. Okay, so just think of two surfaces pressing against each other. You're going to have normal forces in that sort of situation, right? All right, what about tension? We encounter tension whenever there is a pulling force that's being transmitted along an object. But for the most part, we think about tension in the case of ropes and strings and things like that, okay? Now friction is the force that slows things down, that opposes sliding motion between surfaces. And we have static and we have kinetic friction, right? So static friction occurs, preventing actual movement between the surfaces. So when we have static friction, there actually is no sliding motion that's happening. When we have kinetic friction, there is sliding motion happening. So they're both given by very similar equations, but different coefficients, mu(s) and mu(k). And also remember that static friction is an inequality, whereas kinetic friction, we just have the equality between Fk equals mu(k) times n, okay? Where n is the normal force. Does anyone remember like what the values of mu(s) and mu(k) actually mean? Like what kind of information is in those values, in those numbers? Right, but it basically tells you how rough or smooth the surfaces are, right? So low mu values would indicate very smooth surfaces with very low friction, and higher values would be rougher surfaces, right? Okay, so let's get into an example then. First example is this. We have 3 blocks, M1, M2, and M3, which are sitting on a flat surface. Let's say you go ahead and you push this block with a force of 18 newtons. So P is going to indicate the force that we exert on block number 1, okay? And let's just jot down the masses. The mass of the first block is 5.1 kilograms. The mass of the second block, 2.3 kilograms, and then 1.3 kilograms for the third. So let's say that this surface that they all rest on is completely frictionless and that they all remain in contact throughout the motion. So what does that mean? It means as I push them, they're all just moving together. They have the same velocity, same acceleration, same everything, right? So a couple questions about this. First, what is the acceleration of the blocks? Second, what is the normal force that block 2 exerts on block 1? So these 2 blocks are touching each other. Their surfaces are pressed up against each other. There's some kind of normal force there, right? And then finally, how long does it take for the blocks to reach a speed of 5 meters per second? So if we assume that they start at a state of rest when you begin to push, as you keep pushing, they're going to move faster and faster. At some point, they'll hit this speed. Question is, how long is that going to take? Okay. So I'm going to do this problem in a lot of detail. I want us to remember how to make a free body diagram. That's an important aspect of any kind of problem involving Newton's laws. So we have 3 different blocks. Okay, I'll draw each one with a little dot. And the one on the left is block 1, 2, and 3 like this, okay? So you guys tell me, the first block, what forces can I identify acting on it?
Weight normal.
Yeah, so right away we should say there's the weight. I'll call this WE1, okay? What does that mean? It means this is a force that the Earth exerts, and it's exerting it onto block 1, okay? Like you said, there's a normal force here. It's a normal force that the table exerts on block 1, right? And actually, this is going to be true of all the different blocks, right? They're each going to have a weight and then a normal force pushing up from the table, right? So they're all going to have the same sort of vertical forces, more or less. So let's just get those down on the picture. This will be WE2. And then this would be NT2. And then finally we have WE3 for the third block, its weight, and NT3 for the third block, okay? But there's other stuff going on too, right? There's horizontal forces. So for the first block, this is the one I'm pushing. So we're just going to call that force P without any subscripts. We know what that means. That's the force my hand is pushing with, right? Is there any other force acting on this block in the horizontal direction? There's no friction.
Force of block 2 on 1.
Yeah, that's it. This block is exerting a normal force on this block because they're touching, their surfaces are pressed up against each other, right? And that's going to go to the left. So this is what I'll call N21. Make sense? So, what about this block right here? What kind of forces are going to be exerted in the horizontal direction on the second block? That's the one that's in the middle, sandwiched in between 1 and 3. Yeah, there's going to be yeah, exactly. The normal force that 1 exerts on 2 is going to be going this way to the right. And in fact, we've just identified equal and opposite force pairs, right? The force that 2 exerts on 1 is equal and opposite the force that 1 exerts on 2. That's the third law. That's what that little slash mark means, okay? It means they're equal strength of those 2 forces. All right, anything else going on with this guy?
Normal 3 on 2.
Yeah, there's a normal force that this block exerts on this block, and it's going to the left. So this is the normal force that 3 exerts on 2, right? Okay, and then finally, if we go over here, what do we have? Yeah, there's a normal force that 2 exerts on 3. And so these are equal and opposite for the same reason, right? So I'll put a little double slash mark to denote that. And is there anything else going on here for the third block? No, I don't think so, right? Because it's not being pushed from the other side. This is the end of the chain of blocks, so it's just that. All right, so how about we try this? Let's apply F equals ma. Let's just do it in the x direction. And let's apply this to each block. Okay, so when we do this, let's say starting with block number 1. Actually, let's do it in reverse order. Let's do it with number 3 first. Let's do block number 3. Okay? So if I take the sum of the forces in the x direction, all right, here's what I'm going to have. Just one force, which I'm calling N23, going in the positive direction if we use this as our coordinate system. And what's that going to equal? It's going to equal the mass of block 3 times its acceleration, which I'm going to call just A. And by the way, they're all moving together, so they all have the same acceleration. So I don't need to separately label them, right? Whenever you see A, that's just the acceleration that applies to all the blocks, okay? All right, now let's do number 2. So now I have one force going in the positive direction, the other going in the negative direction, correct? So I have N12 minus N32. What does that equal? M2 times A, right? So it's the 2 forces in the x direction added together. That equals the mass of that block, which is M2, times the acceleration, which is A, okay? But what I can do with this is I can say, look, N23 and N32 are equal in magnitude. This is basically the third law at play here, right? In other words, this force that I indicated here is equal to this force in terms of the magnitude, right? So what that allows me to do is say N12 minus M3A. I can make this substitution right here because these are the same force here and here, equals M2A. So what does that mean? N12 equals M2A plus M3A. Okay, so I'm just going to put that to the side and maybe use that later. Let's do it for block number 1 now. Remember, all we're doing here is we're adding up the 2 forces going in the x direction, and then we're setting that equal to mass times acceleration, but for block number 1. So what do I have? I have P going in the positive direction, and then I have N21 going in the negative direction, and that should equal M1A, all right? But let's keep in mind that we have another pair of forces here that by Newton's third law are equal in magnitude, right? So this guy is equal to this guy. In other words, N21 is the same as N12.
by the third law. Which means in my formula, where I see n21, I can sub this right here in, and I'll have p minus this whole thing, m2 times a plus m3 times a equals m1 times a. All right? Now keep in mind, what we're trying to do here to start is solve for the acceleration, which it looks like now we can do. We just do a little bit of algebra. So at p equals, I'm going to move all of this over to this side of the equation by adding, okay? So what do I have overall? Just all the masses added together. m1 plus m2 plus m3 times a, all added together. That equals the push force. So our acceleration must just be the push force, p, divided by all of those masses added together. Okay, and that's our acceleration. Now, I admit we did this kind of the long way, right? What I could have done is just treat all of these as just one big object, and then just do F equals ma on that one big object, okay? And I've gotten the same answer. However, I'm interested in what these normal forces between the objects are, so I have to kind of break it down this way to get that, all right? Anyway, let's put the numbers in. The push force was 18 newtons, right? You guys tell me, do you guys remember what the equivalent unit for a newton is in terms of smaller units?
Kilograms meters per second squared.
Yes, kilogram meter per second squared. So now I'll just take that, express it as 18 kilograms meters per second squared, and divide by the masses all added together. That's 5.1 plus 2.3 plus 1.3, and all of that has units of kilograms, right? So we can cancel out those kilogram units and just be left with meters per second squared, okay? And what you get is about 2.069, if you work this out, meters per second squared. So that's the acceleration of all these blocks, okay? So the second question says, what is the normal force? Hold on a second, let me tell those people to show us whatever they're doing. I was a pretty good skateboarder, but making a lot of noise. All right, so we got the acceleration, good. So for the normal force question, we were asked, what is the normal force that 2 exerts on 1, right? We have a formula for it right up here, which is why we did some of this legwork originally, right? That's, what is it? It is m2 times a plus m3 times a. So that's what we're calculating to get this normal force and answer the second question. All right, mass 2, that was 2.3 kilograms. Mass 3, that was 1.3 kilograms. And the acceleration is right up here, 2.069 meters per second squared. All right, so if you crunch those numbers, you'll get 7.45, and the units here are newtons, because it's a force, okay? So that means the normal force between these two blocks right here is 7.45 newtons, right? So we good on that? Okay, let's do the last part. The last part asks, again, assuming we start from rest as we begin to push the blocks, how long is it going to take to reach a speed of 5 meters per second? So any ideas? What sort of equations we should pull out to answer that? Yeah, it's just kinematics. So we'll just use a kinematic equation. Any ideas which one of those kinematic equations might be the easiest one to go with?
First one?
Yeah, so V, good, is equal to, I'll say Vx, because we're moving in the x direction, equals V naught x plus AXT. We can apply that to the whole chain of blocks, right? Okay, so in this case, what is Vx? That's our final velocity.
5 meters per second.
That's what we put in as 5 meters per second, and what do we put in for V naught x? 0, that means we start from rest. What do we put in for the acceleration?
2.069 meters per second squared.
We put in exactly what we found here, right? So you can use the result from Newton's laws in the kinematic equations, right? So we have, 2.069 meters per second squared, and that multiplies t. So it looks like, if we want to know the time, that's just going to be 5 meters per second over 2.069 meters per second squared. And if you do the math on that, it's about 2.42 seconds, okay? So that's how long it takes to get up to that speed. All right, so a lot of stuff going on here, but let me know if you have any questions on this before we move on to the next one. Any questions? All right. Let's keep moving then. So again, that's a summary of the answers: acceleration, force between these two blocks, and then the time it takes to get up to speed. It's all up on the slide. All right? So let's do another example. Let's do this one. So here we have a 1,380 kilogram crate, which is being pulled up a ramp by a motorized winch, as you can see here. So a few pieces of information. We have the coefficient of kinetic friction between the ramp and the crate. Let's say that's 0.41. And let's imagine that the crate is moving up the ramp at a constant speed of 1.34 meters per second. We're also given the angle of the ramp, that's 35.6 degrees. So the question is, what is the tension in the rope? Okay? So before we get to solving the problem, which of course is going to involve drawing a free body diagram of the crate, by analyzing the forces on that diagram, we can determine what the tension is, which is just one of those forces. But you guys tell me, what is the acceleration of this crate? What can we say about that?
0.
It's 0. And how do we know? What's telling you that?
It says that the crate is moving up a ramp at a constant speed.
Yeah, simple as that, right? So if we're just moving at a fixed speed, there's no acceleration, right? That's the whole idea. All right, so with that said, let's draw the free body diagram of this crate moving up the ramp. All right, so what will we have on this diagram? What forces will be present? So weight, for sure, is going to be there. It's going to be straight down, right? This is W. What else do we have?
Normal force.
All right, and how should I draw the normal force? Is it just going straight up or something else? Yeah, so because this sits on an inclined plane, the normal force has to be perpendicular to that plane. So if the plane is tilted, so is the normal force, right? So yeah, it's up and to the left, something like this, right? Maybe making this a bit exaggerated, but there you go, okay? What else do we have? Tension, right? There's a rope pulling this thing. There's some tension in that rope, and that goes up the ramp like this. What else do we have?
Friction.
Friction. Which type?
Kinetic.
Yeah, kinetic friction. So that's F sub K. And what I'm going to do here is use this kind of weird tilted coordinate system that we sometimes use when it comes to ramps. All right, so X is in the direction going up the ramp, and then Y is perpendicular to the face of the ramp, right? All right, and with that, we can see that the kinetic friction, the tension, and the normal force, they're all just aligned with either the X or the Y axes. But for the weight, we have to kind of break this up into components, right? So here's how we do that. This is just something you should remember. If we have this coordinate system and we're dealing with an inclined plane, this is how we break the weight up into the components. So we have Wx going this way, we have Wy going this way. All right, and then this is the angle of our ramp, which we're calling theta. Okay. So let's just write down what you guys said earlier, right? Acceleration is 0. That means ax is equal to 0. So the acceleration up or down the ramp is 0 as we move at a fixed speed. But it's also true that ay is equal to 0. That's just because we don't come off the ramp, right? So as long as we stay on the ramp, of course, ay is going to be 0. All right. So let's do a little bit of work then. I know that at some point I'm going to need to know what is Wx and what is Wy. I'm going to have to be able to get those components out, right? So how do I do that?
W cosine theta for trigonometry.
Yeah, well, it's going to, yeah, right. It's going to involve our sines and cosines. In case you don't just remember what the result is, you can always work it out, right? You can always work it out just by remembering, okay, sine. What is the basic definition of sine?
Opposite over hypotenuse.
Yep, so that's opposite over hypotenuse. And what's the opposite side in this case? That's going to be Wx, right? What's the hypotenuse? That's going to be the magnitude of the force, which I'll just call W. So that means Wx is the magnitude of the force times sine of the angle, which is, what is the magnitude of weight? mg. That's just mg sine theta, right? And we can say, for similar reasons, I'll just put dot, 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 that Wy is going to be mg what? Cosine theta, right? So you can work it out from the definition of cosine. I'll just leave that to you, okay? So, that's all good. Let's now do F equals ma in both directions, okay? Let's do it in the y direction first, how about? So the net force acting on this crate in the y direction is equal to the mass of the crate times the acceleration in the y direction, right? So how should I look at that sum of forces in the y direction? We have the diagram, it's all there.
Normal force plus normal force minus mg cosine theta.
Yeah, so for now I'm just going to write this as n minus wy. Okay? And that equals what?
0.
0. There's no acceleration. So the reason I did that is to say the normal force is just equal to Wy, which is equal to mg cos theta. Why did I need to know that? Why is it useful that I know the normal force?
Friction.
Because friction, kinetic friction is going to depend on what that normal force is, remember? So just as like a side note, we'll say kinetic friction, whenever we need to bring this in, is equal to mu k times n. In other words, it's equal to mu k times all this right here, mg cos theta. All right, so when it comes time, we'll use that for our friction force, okay? But before we get there, let's do F equals ma in the x direction. And again, just looking at the diagram, that will spell out exactly how you're supposed to put this equation together. So what forces do we have in the x direction, and how do they add up?
Plus t.
Yeah, so you have positive tension going in the positive direction, right? And then we have two forces going in the negative direction, right? Which are?
Negative fk and negative wx.
Yeah, so you see that? T, Fk, Wx. Those are forces that act in the x direction. We have the appropriate signs here, right? And then what does that equal? M times A? 0. So it looks like the tension we are looking for, T, is equal to, just put these on the other side as positive terms, Fk plus Wx. But check this out, we have both of those things. This is Fk, this is Wx, right? And so let's put those in. Kinetic friction is mu k mg cos theta, right? There it is. We worked that out earlier, plus Wx. That's mg sine theta, isn't it? So now we have something we can just plug some numbers into, okay? Mg is a common factor, so I'm going to just pull that out. We have mg times mu k cos theta plus sine theta. Okay, now we'll put the numbers in. What was the mass of this crate? 1,380 kilograms. What's the value of g here?
9.8 meters per second squared.
Yep. All right, and then we have mu k. So that's the kinetic friction coefficient. That's 0.41. And then we just have that multiplied by cosine of the angle of our ramp, which was 35.6 degrees. And then simply add to that sine of the angle of our ramp, which is, once again, 35.6 degrees. Crunch those numbers, and you'll get the tension that's needed to pull the box up the ramp in this way, okay? Did someone do that number crunching for me? Turns out to be a large tension. So let me know when you get it.
Is it 12,400?
Yeah, 12,400. And we can see the units work out to newtons, right? Because we have kilograms times meters per second squared, and then this is all just unitless. So that's how much force would be required to pull it up the ramp, right? Okay, any questions on that one? So hopefully this is looking familiar. There's the answer. Let's keep going, okay? So we covered kinematics, we covered Newton's laws, we did a few examples of all those things. The next topic we hit on in the class, I'm going kind of in chronological order, is uniform circular motion, okay? So we've been dealing with this in the gravity chapter, that's pretty recent, but let's just remind ourselves of some of the stuff and then do an example. So when you have an object moving in a circular path, even if its speed is constant, okay, if we're moving in a circular path at constant speed, you actually are accelerating, and that's because you're constantly changing direction, right? Remember, what it means to accelerate is your velocity is changing. So that can mean you're speeding up or slowing down, like the magnitude of your velocity is changing, or that can mean the direction that your velocity vector is headed towards is changing. That's the case here. When you're moving in a circle, your v vector is constantly changing direction. All right, so we derived this. The acceleration that we're talking about here is called the centripetal acceleration, and it has a magnitude, which is v squared divided by r. Okay, so that's just the speed squared divided by the radius of the circle. We call it centripetal because it's going inwards. Okay, so it's, in other words, seeking the center. That's what the word centripetal means. All right, so we have this idea that objects moving in a circle like this are accelerating, and the acceleration goes inwards. It's not too much of a stretch to then think about what happens in the context of Newton's second law, where F is equal to ma. So
the acceleration is going inwards, so is the net force. If you just look at F equals ma, it's pretty easy to convince yourself of that, right? So what we typically do in a situation like this, just in terms of problem solving, is we apply Newton's second law to what's called the radial direction, okay? And the positive radial direction, just by convention, is taken to be going inwards, and the negative radial direction is going outwards. So any force that's pulling something towards the center is a positive force. Anything that's pushing it away outwards is a negative force, okay? So we have F equals ma in the radial direction, just like we can do it in the x or the y direction. So that means the net force in the radial direction is m times, what's our acceleration? It's v squared over r, right? So all circular motion problems that we've seen are solved in this sort of way, okay? So let's do an example. Let's do this one. This is the tetherball example. We did this in class way back, and I'm kind of changing the question slightly, but we've seen this basic setup where you have a tetherball connected to the top of a pole by some kind of string. So let's say the tetherball has a mass of 1.05 kilograms, and the length of this connecting string is 1.35 meters, right? Let's say it's just moving in a nice circular path around the pole like this. So we set it in motion so that it's moving in a circle like this. And we'll give the angle that the string makes with respect to the pole. So that's going to be 14.5 degrees right here. So a couple questions. Number one, what is the speed of the ball in meters per second? How fast is it actually moving in this circle in order to make this kind of angle, okay? And then secondly, what is the tension in the string? So we'll answer both of these. So as always, we're going to start with a free body diagram. So you guys tell me, what's going to appear, what forces are going to be on the free body diagram of the tetherball? Tension. And which way will the tension go?
Would it go at an angle?
Yeah, it's going to go along the string. So whatever angle the string makes, so will our tension force, right? And then what else? Tension.
Weight.
And weight. Yeah. Is there anything else going on here? I don't think so. So the forces themselves are pretty simple, but it's a little tricky to put them together in this case, right? So we just have the tetherball, and then the tension going along the length of the string like this, and then the weight going straight down. That's all that's happening. And what we should do is set up some kind of coordinate system to work in, okay? So I'm going to use a coordinate system that looks like this, where the y-axis is going straight up, and then this is the r-axis. So this is the radial direction, right? Because going this way, we're going towards the center of the circle that this thing is moving in, right? All right, so that means the weight is just in the y direction, but the tension has both vertical and radial components. So we can say this is TR, this is TY. By the way, this angle up here is theta, the one we've been dealing with before, right? So just like in the previous example, it's probably going to be helpful, right, to know what those components are, how they break down. So let's go through that work. Let's do, how about this time, let's say cosine theta. What's the definition of cosine theta again?
Adjacent of the hypotenuse.
Okay, so it's the adjacent side divided by the hypotenuse. And in this case, what is the side that's adjacent to the angle theta? Right, so that's Ty. And the hypotenuse, that's the overall amount of tension. We're just going to call that T. All right, sound good? So that means Ty is T cosine of the angle theta. And you could probably guess TR is what? The tension times what?
Sine theta.
Yep, just times sine theta. Okay, so that's how this particular force breaks down into components. We have that. All right, so again,
like always, it's time to do F equals MA, and we can do it for each coordinate direction. Let's start with Y. Let's say I want to find the net force in the Y direction. So that's going to equal the mass of the tetherball times its acceleration in the Y direction, right? So forces in the Y direction, which forces on my diagram go into that sum right there?
Ty minus W.
Yeah, just Ty minus W. And what does that equal?
0.
0. So there's acceleration in the radial direction, but there's no acceleration up and down, right? It just stays at a fixed height. There's no acceleration in the vertical direction, okay? So what we can do here is plug in everything we know. Ty, that's the tension force times cosine of the angle theta. And then W, what's that again?
MG.
That's just mg. And that equals 0. So then I can solve for the tension straight away. I'll add the mg term to this side and then divide out the cosine theta term. So it's mg divided by cosine theta. Just like that. And we can plug some numbers in and answer the question, how much tension is there in the string? We can do that part. So, okay, the mass, that was 1.05 kilograms. G, that's 9.8 meters per second squared. And the angle was 14.5 degrees, right? Okay. Someone get a calculator out, tell me what that is.
.63.
Yeah, it's about 10.6 newtons. That's how much tension is in the string. It's a force, right? Okay, the other question, remember, was how fast is this thing moving? What is V, in other words? So, we do F equals ma in the radial direction. That should answer the question. So we'll do F equals ma in the radial direction. And there's only one force, that's TR. Okay? So TR is equal to mass times acceleration, but acceleration in the radial direction, what's that again? What do we put in for that?
V squared over R.
That's where the V squared over R comes in. Okay. Looks pretty good. So one other thing we can do here is think about R, right? So do I know the value of R, the radius of the circle? Do I know what that is? Let me go back to the picture we were given. I know the length of this string. Do I know the radius of the circle we move? Is this a number that's in that text right there?
No.
So what is a number that we know is L, right? So how can I work out R, given that I know L and that I know theta? It's just a little bit of trick, right? Any guesses?
Using sine.
Yeah, L is my hypotenuse right here, and R is my opposite side, right? So that means R is going to be L times sine of the angle theta, right? We can work that out. Okay, so because we have this right triangle, where we have L, the length of the string, R, the radius of the circle, and theta, the angle of the string, you can work out that R is L sine theta. Okay? All right, good. So here's what I'm going to do with that. I'm going to say TR is equal to T sine theta. That's a substitution that we worked out up here. And then I have M times V squared divided by R. which is L sine theta, which is right there. Now, I'm trying to solve for V, right? So, here's what that's going to look like. V squared. That's going to equal the tension times L. So I'm multiplying the L across over here. Then I'm dividing out the mass. So dividing this out puts it over here. And then multiply this sine theta out. Now we have sine squared theta, right? We have two sine theta terms, okay? So if I want to solve for V, I better take the square root of what I just wrote down, correct? So take the square root of that. V is the square root of, I have T times L divided by M. And then if I take the square root of sine squared, then that just goes right back to being sine, okay? And now we can plug some numbers in, okay? So tension, that was 10.6 newtons, 10.63 if you want to keep that extra digit for a little bit of more precise calculation. Newtons are kilograms meters per second squared as a unit. Okay, L, that's the length of the string, 1.35 meters. M, that's the mass of the ball, which is 1.05 kilograms. So remember, we're square rooting all this stuff right here. And then we're just multiplying that by sine of the angle, which is 14.5 degrees. Okay? So that's the number crunching. And it's going to be if you do this, it's going to be 0.926 meters per second, okay? So there's about 10.6 newtons of tension in the string, and the ball is moving at 0.926 meters per second, okay? Any questions on this one? Okay. All right, so those are the answers up on the slide. By the way, I'm already seeing that we have 30 minutes left, so we're definitely not going to get through all of this. So if you take a look at these slides at home, all the answers will be up here. So these are good problems to practice with, even if we don't get to all of them. Anyway, next topic is gravity. So when we talk about gravity, we have sort of two equations that we learned about, all right? And one of them is not so general. It only applies when you're basically standing on the surface of the earth or some other body. And then the other one is a more general form. So near Earth's surface, let's think about that. Objects will feel a downward force. We call this the weight. W is equal to mg. We've been working with that equation today already. G, of course, is 9.8 meters per second squared. That's lowercase g, by the way. However, in general, whenever you have two massive objects, there is going to be a gravitational attraction between them. Okay, even like small objects that you see in front of you. There's a gravitational attraction between me and this box of masks. Okay, it's tiny and it's usually completely negligible, but it's there. It's only when really massive objects are at play that you can actually notice the force of gravity, but it's always there. So the general description of that force is like this. We have two masses, M1 and M2. If you want, you can think of these as like, you know, a planet and a moon orbiting that planet, something like that. Okay, well, on the diagram, we label R as the distance between the two. And if you want to be more specific, it's actually the distance between the two centers of the object. So the force that they're attracted by is given by this equation. This is the law of universal gravitation. This says the force of attraction is equal to big G, capital G, totally different from that lowercase g up there, times m1 times m2 divided by r squared. So of course these are the two masses. R is the separation between the two. And this big G is a constant. It's equal to 6.67, 10 to the minus 11 newtons meters squared per kilogram squared. Okay? So that's what we have. Let's do an example. So in this example, we're dealing with a two-body orbit. So that means we're combining what I just showed you, which is the law of universal gravitation, with circular motion. Okay?
So here's the question. I think I gave basically this question on the test, right? So it's worth going through. We have a mysterious, newly discovered planet that has a radius of 6,500 kilometers, like this. The mass of that planet is 4.5 times 10 to the 23rd power kilograms. So that's the mass. We'll call that big N for the planet. So what we want to do is launch a satellite so that it's in orbit around this planet. So it's just moving in a nice circular orbit at an altitude of 250 kilometers. That is above the surface of the planet, how far the satellite is. Okay, so 2 questions. If we want to get the satellite to orbit at this height, how fast should it be moving? In other words, at what speed do we need to launch it in this direction to start that orbit? That's called the orbital speed. And what is the orbital period? So how long does it take to go around in one complete orbit? We'll measure that in hours. All right, so we'll do this. So the basic picture you should have is, again, you have the planet. I'm going to draw on my picture the planet itself with a solid line, and I'll use capital M to denote that mass. Okay, and then with a dashed line, I'll show the orbit of the satellite, and I'll call the satellite little m. Okay? And obviously in this case, big M is much, much bigger than little m. So let's label a few distances here. This is R. I'm going to call this capital R to be specific. That's the radius of that planet. And then this is what I'll call H. That's the altitude of the orbit. Now, the distance from the center, by the way, okay, the distance of this satellite to the center of the planet is the sum of these two. And that's what we actually care about in our equations. So lowercase r, distance from the center, is equal to uppercase R plus H. It's that full distance from the center that comes into play when we talk about the force and the radius of the path and all that, okay? All right, so let's just put a number to that to start. The radius of the planet was 6,500 kilometers, right? And the height of the orbit was 250 kilometers. So put that together, you get 6,750 kilometers, or what's a kilometer? What's the unit prefix kilo telling us? If I wanted to put this in meters, how would I, go from kilometers to meters?
Multiply by 1,000.
Yeah, so kilometers is 1,000 meters, or 10 to the 3. Right? And so when you do that unit conversion just by multiplying this by 1,000, it ends up being 6.75 times 10 to the power of 6 meters, okay? All right, so that's what we have. Now, let's try doing this. Let's apply Newton's second law to the satellite. So that means F equals ma. Let's actually label the force that's acting on this mass. It's just gravity. Force of gravity attracting it to the planet and nothing else, okay? So what we do is we say the net force in the radial direction equals the mass of this satellite, which is little m, by the way, times the acceleration in the radial direction. We're doing this because we have circular motion, okay? So there's only one force, it's gravity, and the force of gravity is described by big G, big M times little m. That's just the two masses multiplied together, divided by r squared. That's, again, the distance to the center. Okay, that equals m times the acceleration. What's that again? We just went over this.
Square R.
V squared divided by r. Yeah, that's right. So little m drops out. And also, we can cancel out one of these r factors to say v squared equals g big M divided by r like this, okay? So if I want to know the orbital speed v, just square root that. Just take the square root of big G, big M divided by r. All right, so let's put the numbers in now. We have 6.67, 10 to the minus 11 is big G. Units are newtons, meters squared per kilogram squared. Big M is the mass. That's 4.5, 10 to the 23 kilograms. And then divide that by this radius, which is 6.75, 10 to the 6 meters. So square root the entire thing, and you'll have your answer. Okay? By the way, make sure when you're doing a calculation like this is something that I saw missed on the last test quite a bit. We want to make sure that this has units of meters. If we plug this in with kilometers as the unit, that would be inconsistent because I have units of meters here and I need unit consistency between all the terms, okay? Anyway, do this and you'll get 2.109, 10 to the 3 units are meters per second. So if we wanted to at this point, we could convert that to kilometers per second because 10 to the 3 meters is just a kilometer, right? It's 2.1 kilometers per second. So that would be the orbital speed. Okay, how do we get the orbital period? We know how fast this thing is moving in a circle, and we know the size of the circle. How do we get the time it takes to move in a circle?
Use v equals 2 pi r over t.
You got it, that's exactly right. So, and you know, I'm going to take it a step back even from there. I'm going to just say speed. One of the first equations we ever wrote down in this class is speed is distance traveled divided by time, right? So yeah, what that works out to is v equals distance. Well, we go one full lap around this circle. So distance is equal to 2 pi r, circumference. And the time is equal to what we call capital T, the period. Okay, so you move through one circumference in one period. So the value of t, if we just shuffle the terms around, is 2 pi r divided by v. So now we'll plug in what we know. 2 pi times the radius. The radius was, let's do it in kilometers. Let's say it's 6,750 kilometers. Okay? Now to get unit consistency, I need v to be in kilometers per second, but we have that. That's 2.109 kilometers per second. So it looks like if we crunch these numbers, we'll get the orbital period in what unit? What's the unit I'll end up with? Yeah, kilometers cancel, seconds goes to the top. And can someone crunch those numbers and tell me how many seconds?
Twenty thousand 139.
20,100, 109 seconds. How do we get that into hours? The question asked what the period is in hours. So seconds to hours, how do we do that?
1 over 60 times over 60.
Yep. So in every 1 minute, I have 60 seconds. Seconds cancel. Okay. Every 1 hour, I have 60 minutes. Minutes cancel. So just take 20,109 divided by 60 twice. And what do we have? Yep, so it takes 5.6 hours. And that's pretty typical, you know.
Remember, we did this example problem with satellites orbiting the Earth at low Earth orbit, and things like the International Space Station, for example. They take about 1.5 hours to orbit the Earth. So that's a reasonable value, right? Okay, so to summarize that, those are the answers. 2.1 kilometers per second and 5.6 hours. Okay. Let's do another one. In this one, we have the planet Venus, which is really similar to Earth in terms of its radius and its mass, pretty close to the same size. So the mass is 4.87, 10 to the 24 kilograms, just a little bit less massive than Earth. And the radius is 6,050 kilometers, so just a little smaller than Earth. What we're going to do is estimate lowercase g, that's the free fall acceleration on the surface of this planet, okay? So here's how we're going to approach this one. When we talk about the free fall acceleration, we're imagining there's some object in free fall near the surface of this planet. So the planet is big M, its radius is big R, that's our notation. And then we imagine we have some object much smaller than the planet, let's call it little m, and it's in free fall. So you can literally imagine just dropping some object, you know, so that it falls to the surface, okay? So the situation here will be, we have a gravitational force going inwards, right? But we don't have circular motion, right? This is not an object in orbit. Just think of this as an object falling straight to the ground, okay? That'll be easier to sort of visualize. So if we take that and we apply the second law, Newton's second law, to the free-falling body, here's what we'll get. So that's just, again, F equals ma. I'm going to write it in the most generic way, F equals ma. Where the force is this. It's big G, big M times little m divided by the distance squared. But the assumption here is you're really close to the surface, okay? So you're not some large height above the surface, meaning we can just use the radius of the planet for this distance here. Does that make sense? Like, for example, if I'm talking about the Earth, and I just pick something up so it's a meter above the surface of the Earth, that really makes no difference, right? Because the radius of the Earth is so big compared to that. Now, on the other side of the equation, I have little m, and then I'm going to put in here lowercase g, because lowercase g, by definition, is our free fall acceleration, okay? That's all it is. It's just a special case of acceleration when you're in free fall, which means, what does it mean to be in free fall? You guys remember?
The force of gravity is the only force acting on the area.
Yeah. Free fall is just a situation where gravity is the only force that's at play. And that's certainly the case here, right? So what we can then do is cancel out the mass of our free-falling body, which is the little m. And that means g, lowercase g, is big G, big M divided by big R squared, like this. So let's put the numbers in. So big G is 6.67, 10 to the minus 11 newtons times meters squared per kilogram squared. The mass of this planet is 4.87 times 10 to the 24 kilograms. So now I'm going to divide out the radius of the planet squared. So that's, first of all, got to be in kilometers, right? Or sorry, it's got to be converted from kilometers to meters, okay? For the same reason as before, right? We have meters up here, we need unit consistency. So we have 6,050 kilometers. If I do times 10 to the 3,
that'll be the same distance in meters. And then we'll square that, okay? So that tells us how to do the calculation. If you do it, what you're going to get is 8.87 meters per second squared. So remember, the mass of Venus is only slightly less than that of Earth. The radius only slightly less than that of Earth. So it has a pretty similar free fall acceleration, not too far off, okay? All right, so there's the answer, 8.87 meters per second squared. All right, we just talked about this stuff like 2 weeks ago, right? So let's just go right to the example and we'll end at this example here, okay? So this is an example where we are now dealing with the idea of momentum and how it relates to force. Here's what's going on. We have a ball that has a mass of 275 grams, and it's initially moving this way to the left with a speed of 12.5 meters per second. It hits this wooden board, which is kind of tilted, so that after it bounces off the board, it's now moving straight up with a speed of 12.5 meters per second. So a few questions we want to answer here. First, what is the impulse that the board delivers to the ball? Okay. Second, let's say the ball is touching the board for a total of 74.5 milliseconds. What is the average force during that collision that the board was exerting on the ball? Okay. So first of all, we need to look at sort of the initial and final situation. Let's just make sure we're on the same page. Initially, the ball has a momentum that is entirely in the negative x direction. You see that? And then after it bounces off, the final momentum is entirely in the positive y direction, okay? So just keep that in the back of your mind, right? And now we can do the math. So as for the impulse, that's what we call the change in momentum, delta p, which is p final after it bounced off minus p initial, just before it hit. And can you remind me, what's the definition of momentum? When we say p, we can expand that out into what? Mass times velocity. So it's the mass of the ball times its velocity. So we have mv final minus mv initial. Okay. One thing that I saw people miss a lot on the last test was getting to this step, but then not treating momentum as a vector. Okay, momentum is a vector. This is not as simple as just subtracting two numbers, right? We're subtracting two vectors, so we have to really account for that. So here's how we're going to do that. I have mv final. I'm just going to write that vector down. Okay, so the mass is 0.275 kilograms, because 275 grams is 0.275 kilograms. And then v final is a vector, and that vector is only in the y direction, right? That means we could write it as 0 times I hat. And then how fast is it moving? 12.5 meters per second, entirely in the y direction, so there's a j hat there. Okay? Then we subtract on the new line. I'm going to write mv initial. The mass is 0.275 kilograms. And v initial, remember, that initial velocity was entirely in the negative x direction, going to the left. So I can write that as minus 12.5 meters per second I hat plus 0 j hat, okay? And if one of these velocities were at an angle, I would know how to break it down into components using sines and cosines. This example is a little bit more simple than that, okay? So, what do I do? I just subtract down the columns, right? I want my overall x component and my overall y component like this. So for my overall x component, I'm going to have the mass, but then times 0. And then minus the mass times negative 12.5. So those two negative signs cancel. I get something positive here, okay? If you multiply these out, you get 3.438 kilograms meters per second. And actually, if you do the y component, it's the same exact number. 0.275 times 12.5 minus 0, okay? So that's positive 3.438 kilograms meters per second, okay? So those are the x and y components of this thing we call the impulse. If I want the magnitude of delta p, which I'll write like this, it's just the Pythagorean theorem. Just square this and then add to that this y component squared and then put it under the radical. So we have 3.438 kilograms meters per second squared, all that, plus 3.438 kilograms meters per second, square all that, and then take the square root. By the way, you might notice this is the same as just saying root 2 times this number, but this is how we would do it in general. And what does this work out to? It works out to 4.862 kilograms meters per second. All right. Can anyone see what the angle would be for this vector?
45.
Yeah, this vector is at a nice 45-degree angle because it's in the first quadrant because both x and y components are positive, and the x and y components are the same thing, so that's a 45-degree angle. But again, if you wanted to just calculate it, here's what you would do. You would say the angle I'm looking for is the inverse tangent of y divided by x. That's generally how this works, right? So that'd be 3.438 over 3.438, which is the same as the inverse tangent of 1, which is, 45 degrees. Okay, that's the impulse. Both magnitude and direction were found. Okay, for the average force, here's what we use. The average force involved during some kind of collision like this is delta P, the change in momentum that was undergone, divided by delta T. Now, we've done most of the work. There's only a little bit left to go. Can anyone tell me, for the average force, what is the direction going to be in?
Same direction as delta P.
Yep. Same as delta P. How do I know? Just look at the form of the equation. Delta P is a vector, delta T is just some scalar. So if I divide out this scalar, I'm not changing the direction, okay? It's pointing in the same direction. And that is 45 degrees. We already did the work for that. For the magnitude, we can work that out. The magnitude of this average force is just going to be the magnitude of our delta P divided by our delta T, which now we have everything we need to just crunch those numbers. So the magnitude of our delta P was 4.862. Units on that were kilograms meters per second, right? Because it's a mass times a velocity. But we divide out the time interval, which in this case was 74.5 milliseconds. So you guys remember milliseconds or prefix milli, what that is?
10 to the negative 3 seconds.
Yeah, so that's the same as doing 10 to the minus 3 seconds. You got to account for that because we need consistent units here, right? Okay, so can someone do that for me real quick? Tell me what it is. Exactly, 65.3. If we think about the units here, we have kilograms, meters, and then seconds squared downstairs. That's a unit. That's a Newton, I should say. 65.3 newtons. So that's how much force is involved. Okay?
So look, we've got about 5 minutes left. I don't know what to do with those 5 minutes, so we'll just end it here. This is our last lecture, so the next time I see you is going to be for the final in exactly 1 week, okay? So I'll see you then.